Good afternoon. So today I'm gonna work on the exam problem. So
So question 3 there. Question 3 pretty good? Anyone get
I
that?
have not
No?
started grading yet. So I'm gonna start grading.
I can save you a lot of time. Don't bother with question 3. Just skip right over that.
He's not wrong.
All right. I love it.
The woman doesn't have to be a model. She can
All right. The first question is asking for this state of stress, 10,
I have 3 handles.
5 clockwise, and sigma z equals to negative 10. First draw the stress element, and then draw the 3-dimensional Mohr circle. Find the principal normal stresses and maximum shear stress. So first we draw the state of stress, which is a general case. It's gonna look like z-axis, y-axis, and x-axis. So we have 3 planes, 1, 2, 3, totally 6 planes. Just labeling the stress terms that you will see here. Positive 10 in x plane, which is this, it's a normal stress. One axis is going this way. Shear stress in plane x in y direction, making clockwise rotation. So plane x in y direction means going down, making clockwise rotation, tau xy, 5. And one normal stress on plane z, which is this plane, it's negative, so it goes toward the plane. This is the state of stress. We have 3 planes, so we expect to get 3 principal normal stresses. 3 principal normal stresses means no shear stress is gonna show up. So if you look at this plane, in this plane you don't see any shear stress applied to this plane. It tells me sigma z is one of the principal normal stresses. So it's I'm gonna keep this as one of principal normal stresses, and I'm looking for the other 2. So the other 2, if you look at this plane, if you look from this side, you will see a plane stress element like this with sigma x equals to 10, tau xy equals to 5, and these are the other terms. If I want to draw the Mohr circle for this, I pick 2 points, point A and point B, and write the coordinates of point A. Point A has a normal stress of 10 and 5, which makes the clockwise, since the clockwise it should be positive on more circular. So locate point A. Five. Okay, this is point A. And point B is gonna be here. No normal axis, 0, and this one is making counterclockwise, -5. So it's gonna be 1, 2, 3, 4, 5. This is point B. Connect these two. Connect these two, draw a line, circle. Like this. This is gonna be sigma 1. This is gonna be sigma 2. And -10 somewhere here. It's gonna be sigma 3. What would be the value of sigma 1? It's gonna be center plus radius. Sigma 1 is center plus radius. Center is 5, radius is sigma x minus sigma y divided by 2x squared plus tau xy squared. It's gonna be 10 over 2 squared plus 5 squared, which is 7.07. And sigma 2 is center minus radius minus center, If you want to get the right sign, it's going to be C minus R, which is 5 minus 7.07. So this is sigma 3, sigma 2, and sigma 1. Something like that.
How do you know where the smallest circle goes?
We draw 3 more circles. If you know the principal normal stresses, you can connect them. Center is at the middle, and draw a circle with that radius. So what I did, I could find sigma 1, sigma 2, and this one is gonna be sigma 3 because it's gonna be the smallest one. So then I just had 3 circles passing through these 3 points.
Why don't you need the, like when you had X and then you had its shear stress, and it really had the angled line.
Yes.
How come the other ones you just connect through the points on the x-axis? How come they don't have angled?
For the smallest one?
Like, why is the small circle between sigma? I get that Z is a sigma 3, so you start there. But why don't you like connect between there and like where we have Y down 5 on the y-axis?
Because it happens because it's coming from here. Tau zy, tau zx is equals to 0. If they had any terms, then I had to work on this circle to find those points. But since these two are equals to 0, if you look at this plane, it doesn't have any shear stress. For that reason, I'm just working with these 2 points.
Okay, thank you.
Yep. And maximum shear stress. Some of you just introduce the radius of this middle one, this circle, as a tau max. But tau max is always sigma 1 minus sigma 3 divided by 2. sigma 1 is 12 O2, sigma 3 is negative 10 divided by 2, 22.02 divided by 2, 11.01, which is the radius of this circle. Easy. Any question before we go to the next problem? All right. Next problem. We have one internally pressurized cylinder with the closed ends. So we have one cylinder with closed end. Something like this. It's internally pressurized. So we have PI and PO equals to 0. It's not externally pressurized. The thickness is 6 inch. Sorry, the outer diameter is 6 inch. Outer diameter. DO is 6 inch, and the thickness is 1 inch. The question is, what amount of pressure can this vessel carry if the maximum shear stress shouldn't exceed 500 psi.
Wasn't it 5,000? Oh, yeah.
Sorry, 5,000. And after we find PI, what is the state of stress at inner wall? Right here. What would be sigma T? What would be sigma R? What would be sigma Z at R equals to Ri? After we find that pressure. So the first thing that you need to do, you should determine if it's a thick valve or the thin valve. So T divided by R is going to tell us what kind of cylinder we are going to have. T is 1, R is 3, it's going to be 1/3, it's greater than 0.1, it's a thick valve. Yes.
Is it at the inner radius or the outer radius that you evaluate those states of stress? Because you said at the outer wall.
At the end, his last question was,
Oh, no, sorry.
what is it at the outer wall?
Thank you.
But it was maximum.
Okay.
Maximum.
Thick valve. So you cannot start process before checking this because you don't know which equation should be used. So tau max always is sigma 1 minus sigma 3 divided by 2.
Always talking.
That's a really big if there is. It was in a month.
So we should find sigma 1 and sigma 3, and then by dividing 2 set it equals to 5,000, which is the maximum possible shear stress, and solve for P. This is what we are gonna do. So what would be sigma 1? We have 3 stress, sigma T, sigma sigma R, and sigma Z. So since we have internally pressurized, means PO equals to 0. It's gonna look like this for tangential and the radial if it's internally pressurized. This is tangential, it's positive, it's always tensile. This is radial, it's always negative. And sigma Z, which is the last one, where we have the cap, it's gonna be pi Ri squared divided by Ro squared minus Ri squared. So sigma T is positive, sigma R is negative, and this one is positive as well. But sigma T is greater than sigma Z. If you look at sigma T, this term times something which is greater than 1, it's gonna make this possible. So if I want to rank them, the greatest is gonna be sigma T, then the middle one is sigma Z, the smallest one is sigma R. So sigma 1, sigma 2, and sigma 3. So this is gonna change to sigma T minus sigma R divided by 2. Now the question is, at which radius we are gonna have the greatest distance, the largest distance between these two. As you see, at R equals to Ri, the distance between sigma T and sigma R is gonna be at the greatest value. So tau max occurs at R equals to Ri. So at the very inner radius, we are gonna see the maximum shear stress. So now I need to plug in R equals to Ri, and for tangential and the radial stress, and subtract divided by 2 and set it equals to 5,000. Sigma T at R equals to Ri is gonna look like Pi times Ri squared plus RO square divided by RO square minus RI square. And sigma R at R equals to Ri is gonna look like negative Pi. If you plug in R equals to Ri, you will get negative Pi. Just plug in R equals to Ri. R1 minus this is gonna be Ri squared minus Ri squared. We can cancel them out with one negative. Ri squared can be cancelled out, so what is left is gonna be negative Pi. Tau max is sigma T, which is Pi. Ri, RO equals to 3 inch because the diameter is 6. RO equals to 3. 3 minus 1 inch is going to be Ri, which is 2 inch. 4 plus 9 divided by 9 minus 4 minus Pi divided by 2 equals to 5,000. So Pi times 13 divided by 5 plus 1 divided by 2 equals to 5,000. Solve for Pi. Pi would be 2187.5 psi. So this internal pressure is making this maximum shear stress, which is the maximum shear stress. Question on this so far? So after we find this D, I ask you to find the stress terms at the outer radius. This means at R equals to R. Oh, as you see, for radial stress it's gonna be 0, but if you want you can check. Just plug in R equals to RO, do the math, you will get 1 minus 1, 0. Find the sigma T at R equals to 3 inch. It's gonna be just plugging the numbers there. Ri is 2, which is 4 square. Pi is 2187.5 divided by 9 minus 4 multiplied by 1 plus and 9 divided by R is RO, which is 9. This is going to be 2. So the tangential stress is going to be 5,625 psi. Sigma R is 0, and sigma Z, since we have closed ends, we should find sigma Z as well. 87.5. Ri is 2, Ri squared divided by 9 minus 4. 2812.5 psi. 3 terms of the stress for this cylinder at the outer radius. Any question on this? All right. Any question about this?
This another one.
But that question was impossible.
So that's what I thought. Yeah.
So now let's look at problem 3.
That's so sad.
Said here, here's numbers, plug in this equation. I wish ours figured out the order to do it. Like,
All right. There are two forces applied to pipe AB. This is pipe AB, and we know that inner radius and outer radius and inner diameter of the pipes are given. First of all, we were asked to determine all stresses applied at point A and B. So this is the first thing that you need to work on that. So point A and B both located on the same section. So they are not in different sections. It means all loads would be the same for both point A and B. So you don't need to calculate twice for the loads. But the stresses might be different. But for calculating the loads, you just need to do once. So when I'm saying loads, it includes axial loads. Axial loads making normal stresses. Shear force. Axial force. Load, yeah, load is fine. Shear forces, they making transverse shear stress. It can be bending moment. Normal bending, normal stresses. And bending moment can be about two axes. If this is axis Y, it can be about axis X or axis Z. And torsion or torque. It makes shear stress due to torsion. So the key point of on this problem is finding the loads. The rest is just calculating the stresses based on the loads that we apply to sections A and B. So let me start with this force. This force at this section is making reaction in axial direction, which is y. In opposite direction, I say Fy equals to, this is 1500 downward. Here it should apply upward. The direction is J. Y-axis means going up.
There's J's.
This force is making 1200 Newton. Here at this cross section, we should apply the 1200 in opposite direction, in x direction, positive 1200 I. So this making transfer shear, this making normal stresses. Now bending moment. This force times this distance. Force in y direction, distance is x direction. So it's making z direction moment. Mz is, yes,
Shouldn't that be F Z 12 times I?
thank you. F in z, thanks. In k,
That's something on the speed
thanks for checking. So it's making moment about z-axis because distance is in x direction, force in y direction, moment is going to be in z direction. Force is 1500, the distance is 45 millimeter. It's going to be 67.5 Newton meter. Now, this force has two distance. I mean, has a distance in two directions from this section. One is this distance in this direction, and the other distance would be in y direction. So, this force times this distance is making, this is in z direction, distance is x direction, so it's making about y axis. So my would be force times this distance times 90. And this force times this distance is making rotation about x-axis. The force is going in z direction, the distance is about y-axis, so the moment is going to be about x-axis. So mx would be 1200 times vertical distance, which is 75 millimeter. Any questions so far? Alright, now this load applies to section passing through point AB. Now I'm gonna look at the S stresses that each load is gonna make at each point. S stress says at point A. Let me start with this one. For point A and B, it's going to be under compressive loading due to this. So sigma axial is gonna be force divided by area. Force is 1500 negative because it's gonna be compressive stress. Area would be pi dO squared minus di squared divided by 4. It's a pi, so you need to find the area that we have the
Just one
No.
So it's gonna be, let me find the area first here. I'm gonna use this. Area would be pi over 4 dO squared minus di squared. Outer diameter is 42 millimeter, 10 power negative 3. Inner diameter is 35 millimeter. It's gonna be 4.2 10 power negative 4 meter squared. So dividing by this area is gonna give me negative 3.54 megapascal. Point A is gonna see this axial stress. Point B is gonna see the same thing because the load is not going to change, the stress is going to be the same, but we are focusing on point A. Right? So now I'm looking at the shear stress due to transfers, due to this shear force. I'm looking for point A. The shear force is going to apply in this cross section. So point A is not going to see any transfer shear because if you remember when one cross section is under transfer shear, this point is gonna see the zero transfer shear, and this any point in this section in this line is gonna see the maximum transfer shears, which is equals to to be divided by the area. For the cross section that I have, as you see, the maximum shear stress occurs at the middle point, which is point P, located on that, and point A is gonna see the shear stress equals to 0. So transfers. So I'm done with these two. This one is making so this one MZ. MZ it's gonna be about z-axis. So bending moment about z-axis. So it's rotating about z-axis. If bending moment is about z-axis, the neutral axis is gonna be here. So point A is gonna be there. So it's not gonna see any normal stress due to the MZ. So I shouldn't be worried about this. But MY, it's making rotation about MX. MX is making rotation about x-axis. So the neutral axis is gonna be this. So point A is gonna see the maximum normal stress. Sigma is gonna be MC divided by I. MX is 90. C is RO divided by 2. And I is pi divided by 64. DO power 4 minus DI power 4. You need to calculate this, which is 7.9 10 power negative 8. Ninety times outer diameter is 42 divided by 1 by 2 is gonna be 21. .38 megapascal. So the last load that I should look at is My. Axis of this part is Y, and is about y-axis, so it's a torsion. So tau is gonna be Tc divided by J. T is My. Ro divided by 2, and J is 2 times I. Or it's gonna be pi divided by 32. So it's not gonna. The shear stress is gonna be 14.3 megapascal. So the total shear is gonna be summation of these two, 0 and 14.3. The normal stress is gonna be the summation of these two. It's gonna be 23.92. So 23.92 minus 3.54, which is the compressive, is gonna be 20.38 megapascal. And shear stress is gonna be 14.3. This is 4.8. If I change point A to B, the axial normal stress is not gonna change for point A and B. The transfer shear is gonna change to 2V divided by area, which is 1200. The shear force is 1200 times 2 divided by area, which is given. $5.6 6.71 megapascal. For bending moment, mx doesn't make any normal stress because it's gonna located on neutral axis, point P, but mz. So 90 is gonna change to mz, which is 67.5. And it's making compressive stress at point P. It's rotating in this direction, so point P is going to be under compressive. So it's going to be negative 17.5 megapascal. And the shear stress is going to be the same. On this cross section, if this is point A, this is point B. If this is point A and if this is point B, the torsion is gonna rotate in this direction. So the shear stress here is gonna be in this direction, and point A is gonna be in this direction. And this force is gonna be in this direction, because it's gonna cut, this force is gonna cut the surface from left to right. So it's going from left to right. This is gonna be 0. For this, you should add them up. So shear stress is gonna be 14.3 plus 5.71, which is 20.01 megapascal. And normal stress, -3 here, -17 here. This is for point B.
Dr. Gopi,
Yes.
I know we had slightly more time, but you've taken this whole class to copy down your notes onto the board.
I didn't copy, I just used the numbers.
Well, but you know how to do the test.
At the same time, I explained.
None of us did. And I'm just saying, test may have been a little bit long. Just
I'm
Just
not
just a little bit. Like if I had 3 hours, I might have been okay.
I'm not agree with you. So, I think you had enough time to work on this 3 problems.
Well, 4. I know the last one was bonus, but if no one got to the bonus, is it really bonus? It's like
Some of you worked on that. I just checked.
Okay, so they worked on it, but did they finish problem 3?
yeah.
Did they give up halfway
I
through?
should look at it. I just look at the problem.
I think we should send out a doodle poll. And